Hello all, welcome back to the video 2 for section 1.9. Okay, and as we say here, the rest of the section is dedicated to two important properties of linear transformations. We'll get to those properties right away. A linear transformation is called onto if. Oh, where's my page 2? Here we go. If what? If for each B in Rm, if for each thing in the target of our transformation, we can find something that gets mapped to it. So for each B in Rm, there is an X in Rn, so that T of X is equal to B. Yeah, in other words, T is onto if the equation T of X is equal to B has at least one solution. We don't care if there are lots. We want at least one solution. That's onto. And the next property is its buddy, the transformation from Rn to Rm is 1 to 1. If what? If each B in Rm is right. If anything you grab here, there can't be more than one solution to it over in the other side. So there's no problem if something here is missed, but there's no way that two different vectors would be being sent to the same place. So if each B in Rn is the image of at most one vector in Rn, is the image of at most one vector X in Rn. So in other words, T is 1 to 1 if the equation Tx is equal to B has at most one solution. Okay, so they're both about solutions to this equation, whether there's always one or there's never more than one, basically. Okay, so let's look at an example and figure out if the linear transformation here is 1 to 1 or onto. Boom. Okay. So then solution here. Oops. So let's worry about 1 to 1 first. Okay, and we notice that there are more. Oops. There are more columns than rows. So we know that in particular, our columns have to be linearly dependent. So since there are more columns than rows, yeah, the columns must be linearly dependent. Must be linearly dependent. Okay, so then this means, among other things, that the equation AX is equal to 0 has a non-trivial solution. That's sort of the definition of linear dependence. And in particular, since there's a trivial solution and a non-trivial solution, this equation has two solutions, which means it can't be 1 to 1. Right? 1 to 1 means that for anything we pick in Rm, in our target, there can be at most one solution. So here we picked B, we saw that there are two vectors being sent to B, both the zero vector and some non-trivial solution. And so it can't be one-to-one. So this means that, yeah, AX is equal to 0. It has at least two solutions. Two solutions. Yeah, so T is not one-to-one. Tempting to say that A is not one-to-one, but that isn't quite what we mean. We really want to be talking about the transformation. Okay, now let's check and see if T is onto. So yeah, to determine if T is onto, we want to set up the equation AX is equal to B for an arbitrary B, and see if that linear system is solvable. So we're going to check if AX is equal to B always has a solution. Yeah, for any vector B. Oh, let's give ourselves another page here. Oh, okay. So then we'll do the thing we always do. We know that this matrix equation just corresponds to a linear system, and so we'll set up a linear system where our last column is like B1, B2, B3, or whatever. Okay, so we've got our matrix A, which is 1, 2, -3, 3, 5, -4, -1. Oops, it's all right. 0, 4, 1, -1, 1, 0, B1, B2, B3. Right, and this matrix A came from what was given to us, right? Yeah. It's a 3. Yeah, that's right. Good. Okay, so we've got these sort of variables for our B, and all we're trying to do is figure out, is it possible to get a row of what? All zeros here and something non-zero there. That would tell us that no, there's some values of B where the system doesn't have a solution. Okay, so let's do some row reduction. We're all big fans of that by now. Okay, so let's take row 2 minus 2 row 1. We'll do row 3 plus 3 row 1. And we're going to get, our first row doesn't change at all. Row 2, we've got 0, -1, 4, 3, and then B2 minus 2, B1. And for, adding 3 times the first row to the third row, we're going to get 0, 5, 1, -3, and then B3 plus 3B1. Okay, and we'll do one more. Here, let's do row 3 plus 5, row 2. And actually, I think that'll be enough. Let's see. So our first row is unchanged. Our second row, also unchanged. And the third row is the only one we're going to fuss with. So we've got 0, 0, 21, 12. Now we've got a mess here, but that's life. What is it going to be? It'll be B3 plus 3B1 plus 5 times B2 minus 10 times B1. So we're going to have, how many B3s? It's just a single B3. We're going to get 5 B2 and a net of 7 minus 7 B1. Okay, and now we can see, well, no matter what else happens, there's no way the whole row is going to be 0. We can certainly get a 1 here, and these pivots aren't going to change. So there's no way we're going to get 0, 0, 0, 0, something non-zero. And that's the only circumstance where our linear system has no solution. So since there's no since, yeah, echelon form has no row of the form. So row like 0, 0, 0, something non-zero. Yeah, our system is consistent. Our associated linear system is consistent. Okay, so that means that AX is equal to B always has a solution. Which means that T is onto. Okay, and we can prove a little theorem that helps us, at least helps us with one-to-one in the future, sort of captures some of the, yeah. Okay, so then, yeah, you might, looking back in this example, you might think, well, it was awfully lucky that we happened to find that we happen to know to pick 0 to be our value B. Otherwise, it would be hard to figure this out. And that certainly seems that way. Yeah, seems very lucky that to have looked at what did I even write down there? I think we wanted T of X is equal to 0, actually. To show that T is not one-to-one. But this next theorem sort of clears that up for us. Basically says if, yeah, T being one-to-one is equivalent to 0 having only the trivial solution. So let's let T be a linear transformation from Rn to Rm. And then, yeah, T is one-to-one if and only if just this equation has only the trivial solution. So this means that just showing that a linear transformation is one-to-one just means we only ever need to worry about how many solutions are there to T of X is equal to 0. So that really limits, that makes it much easier to show something is one-to-one. Yeah, in practice, we're always using this in the direction in the like working on this equation, Tx is equal to 0 to prove T either is or isn't one-to-one. The other direction is not that useful. Yeah, so this is what I'm saying here. In practice, we use this theorem by attempting to solve T of X is equal to 0. One solution means one-to-one. Infinitely solutions means not one-to-one. And there's never no solution because 0 is always a solution. Okay. And we can do a quick little proof sketch here too, right? If T of U is equal to T of V, then we can just subtract T of V from both sides. Get T of U minus T of V is equal to 0. And since T is linear, this is the same as T applied to U minus V. And so if U is not equal to V, we have a non-trivial solution. To T of X is equal to 0. Okay, so this is just a sketch of the idea. The complete proof is in the textbook, and I encourage you to look up the complete proof if you're so inclined. We have another little, yeah, we can collect some of the strategies we used in that previous example into a theorem here. Okay, so let's let T from Rn to Rm be another linear transformation. I'm saying the word transformation there, but you know. Okay, so let's let A be its standard matrix. Then T is onto exactly when the columns of A span Rm. And T is one-to-one if and only if the columns of A are linearly independent. We can give a little proof sketch of this too, I think. Okay, so then for part A, it's theorem 4 that says the columns of A spanning Rm is equivalent to AX is equal to B being always consistent. Okay. Yeah, but this means since T is representing or is represented by A, this means T of X is equal to B always has a solution. So T is on 2. And for part B, yeah, A having linearly independent rows, columns, linearly independent. Means what? AX is equal to 0 has only the trivial solution. And so by the previous theorem, by theorem 11, we get that this is equivalent to T being 1-to-1. This is, yeah, both of these are more or less complete proofs, but again, the textbook has more details if you're interested. Okay, that's it for 1.9. I'll see you all with section 2 next time. Take care.